The purpose of the course is to give you the briefest of introductions to geotechnics, which is geotechnical practice, which is soil mechanics, rock mechanics, engineering geology, geohydrology, and slope stability, and engineering seismology. It's a lot of different, it's very, very multidisciplinary. And what I'm trying to give you in the lectures is just the stuff that isn't in typical textbooks based on my 25 years of experience before I came here as a full-time academician. So I expect you to read the book to get the language. The book has basic chapters giving you an introduction to that subject matter. And all we're trying to do there is to expose you to a lot of these things. So when somebody says stereo net and says wedge failure, or can you define a wedge, you have some idea what they're talking about. We're not going into enough detail on any of this stuff to actually enable you to go out and practice in that particular arena. But at least if somebody brings it up at the office, you can say you have some vague idea of what they're talking about. So that's the kind of stuff we're trying to touch on. So I'm not concerned about whether you got exactly the right answer according to the back of the book. You know, if the slope can be 74 degrees or 68 degrees. In our business, 68 and 74 is the same answer. That's close enough. We don't do things with a greater tolerance of that, despite what some teaching assistant in your field geology class may tell you. When you're taking strike and dips measurements up at the Earth's surface, they are incredibly biased by slope creep and weathering. So they're not reliable for projecting any great distance into the ground, like more than 50 feet. They're not reliable for that. So drillers know this, but most college graduates don't, because they don't spend as much time out in the field as the drillers do. So don't get worried about whether your answer is exactly like what's in the book. What I look at is like what any boss looks at. I look at to see if you put effort into it. That's what I look at, effort. So not worried as much about the answer as the effort. Okay, with that said, we have to have a brief introduction to what stereographic projection is. So I brought some toys along with me today, some visual aids, and ooh, that's a good one. Somebody's doing something out there in distance learning land. Okay, we have a sphere. See the sphere. And what we're doing with the stereographic projection stuff is we're taking half this hemisphere, the lower half, and we're representing it with a stereo net. And what we're trying to do in 2 dimensions is try to do a little bit of 3-dimensional analysis. Now, everything that we do in geology is very 3-dimensional. It's very complex. It's using the artistic side of your brain instead of the abstract reasoning mathematical side of your brain. So for all of you who max the ACT in mathematics, you're the ones that are going to have the greatest trouble with this, probably, because this is spatial, or we call structural visualization. You're trying to visualize things. So if we have some sort of inclined surface, let's say we have a bedding plane that's dipping 45 degrees. If we look in a lower hemisphere projection, there's 45 degrees. Now, if we look at it in 2 dimensions, it looks something like that. It looks like a quarter moon, if you will. I'm trying to get this right for the camera. Boy, that's tough. All right, so what I'm doing then is plotting these various strike and dips of these perfectly planar surfaces, and we're trying to show those in a graphic representation on a stereo net. So let's go over to our camera over here, our table. See if we can get this going. Hang on. There we go. And, it's got cellophane on it, so we're going to have some glare issues, I can see here. This is a Wolf stereo net. There's also one that's an equal angle one called a Lambert net, Lambert projection. Back in the old days, we taught everybody surveying and cartography. We don't do that anymore. That's too bad, so we can't talk about these things and just assume you know all these projection issues. But if we take the various data that we were given in the problem and we put this thing on there, we would start out our process by marking N for north, 270 for due west, 90 for due east, and 180 for due south. And then I would up here, just like a word problem in algebra, I would write down the various attitudes of the discontinuity. So he gives you joint set 1, which we call J sub 1 typically, and that's north N 78 E slash 72 north. Now, in order to plot that, I start here at N and I count down 78 degrees east. And I put a dot right here, and you can see I have a 78 right there. That's a note to myself. And so then I rotate this 78 up to the N line, which I don't have a light table here, but that's N right there. And it tells me it's dipping 72 north. Now you have two choices, 72 north and 72 south. 72 north is going to be over here on the N side, the north side. Right there is N. So now I come at the equator line, which is right here now, and I count in exactly 72 degrees, and I get right there, and I scribe the great circle that is striking north 78 east and dipping 72 north. And there it is. It looks like that. And then if I want to, which helps me visualize it when I'm a beginner, I can put a line along the origin like this, which that represents where this plane intersects the half hemisphere at the equator. So now I have something, and it's dipping very steeply like that. So now I come back to N, back to north, and I look at the second one, and it's also striking north 78 east. That only happens in class problems. That'll never happen to you in practice. I've never seen that happen in practice, but it does. It's nice for this one. So now I'm going to rotate back again to the same spot, 78 east. I'm going to put that again going north and south, perfectly on the north arrow. And this one is dipping 78 south. So now I'm going to come in from the east side, and I'm going to count 10, 20, 30, 40, 50, 60, 70, 2, 4, 6, 7, 8. And I'm going to put another one going the other direction. Now these are simply planar representations of a series. This is an average value for a series, a joint set. It's an average for a joint set. And in real world, we're going to have, 10, 12 degrees variance. 0 to 10, 12 degrees variance with the strike and the dip. But that's the average. So now we rotate back to north, and what we see is we have one set dipping very steeply to the north and another set dipping even more steeply to the south. So that's going to be a very tight sliver wedge posed by those two where those two meet. And they're not going to be a whole lot of problem because their line of intersection is horizontal. So they're not going to come spilling out of a highway cut on us because they have the same strike. Okay, joint set 3 is north 17 west and 80 west. Well, 80 again is very, very steep. Okay, so I'm going to rotate to 17, count out 17. Well, I'll start at north. I'm going to count out 17 degrees. I'll mark it 17. Now I'll rotate on a pin here in the origin to N. Now 80 is almost vertical. Vertical is a straight line. So here I'm going to be just 10 degrees off of vertical. And so now I have another, and this is the orthogonal set. This is the one that's kind of 90 degrees almost to the other one. And so that's what you'd expect to see. And now I have 3 sets of discontinuities plotted. Now I rotate back to N, and I look at this, and I say, okay, does that make sense with what I'm seeing out there? Typically, you'll have two sets that are mutually orthogonal to the bedding, and then another set that's maybe not as pervasive if you have bedded sedimentary sequences. Now, if we look at the intersection, this point is the intersection of J2 and J3, so we call that I23. This one is the intersection of J1 and J3, so that's I13. Over here, we're going to have some other intersections we're going to do when we track the bedding. So now the bedding, we have to, that's our fourth one, we have to do that now. It's north 45 east, 26 southeast. So we're going to go north 45. We'll rotate up to there. That might be my phone ring. I didn't turn it off, sorry. And now 26 east is not nearly as severe. So what we're going to do here is we're going to count in and go 10, 20, 2, 4, 6. So here we have a much flatter surface. That's a 2-to-1 slope, by the way, roughly speaking. So we're going to draw this one in, and that's the bedding. Now, a lot of times when I was early in practice, I would do the joints in black and the bedding in brown, just so I can tell them apart. And I can put this one here is just for convention. I can run it across so that it helps me visualize what's going on here. So if I go back and get my cardboard cutout, what I have going on here is something dipping like that, 2-to-1. So if we look at it head on, I can't do that. Looks something like that, 26-degree slope. 2 horizontal for 1 vertical. Now, rotate back to north again, and I can see here I have intersection between the bedding and joint set 2, so that's I2B, and the intersection between the bedding and joint set 1, I1B. And if I rotate this again, I can actually see to the, if I bring this point to the equator line, the east-west line, what I can see here is that's 10, 11, 12, 13, but it's dipping, that intersection is dipping about 16 degrees. That's pretty flat. It's going to be hard for that wedge to slide out unless the phi angle is less than 16 degrees. So not going to be too problematic. Now, the cut. And this is where it gets more complicated. There's 2 cuts. There's the cut on the right side of the road and the cut on the left side of the road. And they're going to have different solutions, but they have the same strike. So we got to remember that. So the problem says, right here we wrote down cut north 17 west. And they're going to tell us that it's the cut on the right side, so the cut's going to be the right side is facing west. How steep can we make this cut slope before we're going to start having some wedge failures? So we count over here, it's north 10 east, The cut is north 10 east. And how steep can it be is the question mark. So we go, all right, count over 10, rotate just a little bit, get that straight. And now we see there's my first intersection that's going to daylight out of the hill. Now what we're trying to do here, let's look real quick. I'll draw this for you. I've got a slope, let's say it looks like this, and I'm going to cut it here for a highway. And I have various intersections like that. Some are like that, and some are even steeper than that. So I can make this cut up to the point where I daylight that wedge right there. And that wedge can slide out on me. Now if I make the cut flatter than this, if I make it the same attitude as that intersection, then I can't get a wedge coming out. And that's what they're asking us. They're saying, well, what's this number right here in degrees from horizontal? That's what they're asking you. So let's go back to our plot. Get us on our pin here at the origin. We'll rotate to 17 to 10 to due north. Now we're going to look down this thing, and there's the only intersection we have. That's the first one we're going to hit. And if we count this out, what we're going to find is that, let's see, I'm going to rotate it to, there is, if I want to get the plunge, this is the plunge, so I'm going to go out on the equator line here, and I'm going to find that that is roughly 10, 20, 30, 48. It's about north, 48 west is the direction it's plunging. And if we rotate to here, we're going to see it's about, let's see, I have trouble seeing through. I didn't use tracing paper, so, but it looks like 10, 20, 30, 40, 50, 60, about 68 degrees is what I got. So if I look at if I draw my cut through that line, which is what I have to do, I'm going to draw my cut through that line and draw a great circle. So I'm going to dash this. This is as steep as that cut can be before you're going to have trouble. So there it is for that strike. They gave us the strike of the cut. Now, if I measure this off, what I'm going to find is it's about 74 degrees right there. So the measurement comes right here, like that, and it's about 74 degrees. So that's as steep as a cut can be. Now, if you have something that looks similar to this, you're on A+. We're not looking for perfection. I'm just looking for you to get exposed to what stereographic projection can do for you. It's a very, very powerful technique to look at things in 3 dimensions. That's the easy part. The hard part is, in the real world, things don't group perfectly. You get a lot of data splatter. So you have to end up looking at the data splatter and contouring the poles to these various planes and choosing averages. And then you got to realize where you're going to get the rock slide is where you don't have something that's average. So it's not foolproof. So statistical things like probabilistic assessment are never going to prevent you from having failures. They only prevent you from having a whole bunch of failures. So sometimes I have to look at the data and say, joint set 1 is very, very consistent. This is the average strike and dip plus or minus 4 degrees. Joint set 2 is a little more diffuse. They're a little further apart. They're not quite as regular. The average change there is going to be up to 10 degrees. Joint set 3 is the wild card. It might be off as much as 15 or 16 degrees. So what I have to do then, joint set 3 is the one that's going to get you. Because if you put your engineering hat on, which is what we all like to do, and go, well, I'll use the average value. Use the average value, you're going to be wrong half the time. Half the time. So you decide, do you want to have the plane crash half the time, or would you rather, be safe? So if you want to be safe, what you have to do is you have to say, well, this is the minimum value we measured out there. Let's run that one. Here's the maximum value. Let's run that one. And we call that, we have a big word for that. It's called a parametric analysis or a feasibility analysis. What we're saying is, under extreme conditions, that joint could be dipping as low as this number, so that's the one I'm going to have to design with. I got to design for the weak link. So always think the chain we put across the Hudson at West Point to keep the British ships from coming up the river in the War of Independence. How strong is the chain? Only as strong as the weakest link. Welcome to rock mechanics. That's why it's so vexing. Soil mechanics is much, much easier. You can almost do it in your sleep some days if you have good data. That's where the kicker is on that one. Okay. Any questions? That was a very quick overview, I realize, but I think it merited that based on how many people came to see me this last week. I had a revolving door going, so I felt like a candidate running for office. So anybody else? Any questions? All right, so work with yourselves on stuff like this. That's fine. I don't want you to just copy your neighbor, but what we do in the real world is we have bull sessions at the end of every day. We don't use that term anymore. That's a passé term, but we have group discussion time. Sit down on the carpet, remember like preschool, and talk about your feelings. And what you do is you talk about things you ran into that day, and you lay it out there for the other people in the discussion. And this is real important for training our young managers who are up and coming. So we want to get in that discussion session and have them just observe, or sometimes have them bring up, well, I ran into this problem today, and what should I do here? I got a few joints out there that really have unfavorable inclinations. Do I really need to incorporate that into the whole analysis? You don't always. Sometimes you get out there and you look at it by inspection. We call that the observational method. And we say, uh-oh, right here, we got a shear zone or we got a fault and it's aberration. We're going to have to do something right here that we don't have to do over here and over there. That's good engineering judgment being exercised. Unfortunately, we don't always have people that smart out getting dirty and dusty and watching the job go in. Usually it's the lower end people that are out there watching it, and sometimes they're not watching real carefully. Sometimes they're smoking cigarettes, sometimes they're texting, sometimes they're having lustful thoughts. They're just not paying as much attention as you'd like them to be paying. So that's not a safety net by any stretch. Okay, let's see. Do I get out of this by hitting that?
I don't think so.
I don't know how to get out of this thing. All right, there we go. Okay. Now we go to removable disk, and we're going to pick up where we were. Anybody remember where we were? Speaking of that. 80? 8. We had to get past 8. Let's see. Do you know what slide number we were on?
I think you stopped at the end.
Okay. It's a big file, so it's going to take. Okay. Talked about strain and compatibility, strength and fracture anisotropy. Yeah, we talked about tensile strength of rock. Wow, it's a big file. Got all the way down through this. Okay. I think we got to right here. That sound right? 81. We were talking about the graben structure. And this graben structure is one of the largest landslide structures in the United States. It's centered around the area where the Green River, coming out of the Wind River Range in Wyoming, meets the Colorado or Grand River coming out of Colorado. And this is over in eastern Utah near the Great Confluence and in Canyonlands National Park. We're actually down in the southern part of Canyonlands, the Needles District, which is on the south side of the Colorado River, just due south of the confluence. And this is an area where a large amount of paradox basin salts have risen up in giant diapirs or salt domes, and then the rivers have eroded that material away, and so there's this collapse feature, and you get these big grabens that are formed because of the collapse feature. Here's a real typical kind of picture you see when you go out in the field and you're looking at an escarpment and you see open joints. Now, the reason I got real interested in all this stuff and got fascinated with all of it was I was a rock climber. And rock climbers look for places they can go up the cliffs, and they have an easy time finding something like this where you can actually jam and just chimney. It's called a chimney. You can just chimney up this whole thing, provided you take some breaks and have some protection for your forearms and whatnot. But what I noticed was that all cliffs seem to be controlled by joints. This cliff you're looking at right here, you're looking right up the strike of this thing, and you can actually see here, there's joint set 1, which continues right here, 2, 3, is all the same joint set, 4, 5, and there's actually a 6th one right there and a 7th one right here. So this is in the Coconino Sandstone, north rim of the Grand Canyon, right below Monument Point. And what you have going on here is a joint controlling the morphology of the cliff, and that's very, very typical. So most of the time if we see a big slick surface or fairly planar surface, it's probably joint controlled. So that's the first set you want to get identified. The bad news is you can't see what's behind this set because it's hidden from your view. And that's one of the things we want to talk about today that is the most vexing problem. And I'm showing it right here. Now what's going on here, this is a very important couple of diagrams. What I have going on up here on top is you see the sugar cube pile. Think of rocks, bedded sedimentary rocks especially, as sugar cube piles. The thicker, stiffer beds, the joints are farther and farther apart, and you see this nice seesaw kind of block structure. And when you look at an aerial photograph, you can actually see all these lineations, which are solutioned joints. And so the water travels through the joints. Water doesn't travel much through the rock itself. If you're going to go out and monitor a place like for groundwater, or you want to monitor it for anything that has to do with fluids, you got to drill angled holes that pierce these semi-vertical joints. Now if you look down here, you have another little bed of sandstone down here, but it's much thinner, so it's less stiff, so it's the same joints, same orientations, but much more intense, much closer together. And that's pretty typical anywhere you go. If we go down the hike down to the bottom of the Grand Canyon, we look in the Cambrian unit down there, the basal Cambrian unit, 570 million years ago, is the Tapeats sandstone. And that's the first unit in a regression sequence of oceans coming in and regressing over the landscape and depositing succeedingly deeper and deeper water sediments. Now, if we look at the systematic regional joints in that formation, they are reflective off the basement rocks, the Precambrian basement rocks that are beneath them. So just like reflection cracks in pavement, when you put new sediments over something that's cracked and you have diurnal earth tides, those cracks are going to open and close twice a day. So you're going to tend to get cyclic loading concentrated. The strain's going to be concentrated on the old joints. So what happens is the new joints form right on top of those. And as we look at the entire Paleozoic sequence in the Grand Canyon, we see the joints reflecting right up through the entire Paleozoic sequence from Cambrian to Permian. Then at Permian time, a whole bunch of things die off, and the continents start cruising around and moving. So the earth tides change, the directions change, and the joints orientations in the Mesozoic units take a shift. that we see in the Triassic, Jurassic, and Cretaceous. And then at the Cretaceous Tertiary boundary, it really goes wild, because that's when Pangea breaks up. And you see those joints have a completely different orientations. Now, they're still orthogonal to the bedding, but they have different strikes. So you want to be observing this stuff. This isn't rocket science. It's just all about observation, about stopping, taking time, and observing. Now, one of the things you want to observe is blocks. If you see blocks the size of Toomey Hall sitting right here, and that's where your client wants to build their dream house, you have to ponder how much you like the client. If there's somebody that doesn't pay their bills, you don't like them too much, I guess you could go ahead and put them right there. But if there's somebody who's been a fairly good client to you, you might want to point out to them, Dr. Muther, there's some really large blocks there in that area. That doesn't look like a real friendly place to sleep at night. You could put your tennis court there, because you're not out on your tennis court all the time. But I don't know, I'd want to sleep there. Now, you'd be surprised how many people are killed in the Grand Canyon every year by debris flows because they're sleeping right in a dry channel on a stormy night. And most of them are college graduates. We quit giving that. Emmett, I don't think we give that degree in common sense anymore. Nobody wanted to take that one. What do you think goes on in channels? Water flows in them when it rains, when there's water there. And in Grand Canyon, the dominant process of transporting material is debris flows, debris torrents. So if you're camping, it's a nice place to camp. It's flat, it's got soft sand, that's all great, as long as it's not raining up above you. Now remember, in the Grand Canyon, the rain's up above, the debris flows are down below. So the people are down there, it's not raining on them, but they have a big thunderstorm up on the rim, the debris flow comes down and kills them every year, every year, every year. Usually they're people from the Midwest, because we don't have debris flows around here. We don't have big mountains around here. So you want to ask yourself, how do these boulders get there? And then you might want to ask yourself, do I want to be sleeping right here or right there? Do I want to be tempting fate? But you do want to look at boulders like this and then look back upslope and see if you can see where it came from. Now, when you see where that rock just came from, we call that scar where it pulled out a mold. That's called a mold, M-O-L-D. A mold is a wonderful thing to look at and put on your stereo net, because you know that one just failed. So that's not a good geometry for stability. So you always want to, first thing you're going to do is you measure the molds and you get those data on your stereo net, if you're going to be designing anything that's near the cliff, like a road. Now, here's the problem. Right here, if I'm in a big canyon, and the canyon's got an orientation like this, and my regional systematic joints are coming out in a seesaw fashion. So my cliff goes in, out, in, out. It's structurally controlled. In, out. And I set up a LiDAR rig out here, and a LiDAR rig costs $100,000. And I can record 20 million measurements in 15 minutes. Wow, this thing's powerful. Yeah, it's powerful. Is it going to prevent rock slopes from failing and killing you? No, it's not. There's some things LiDAR can't see, like anything behind your hand and anything behind the cliff. It's what's behind the cliff that's going to kill you. So LiDAR is great. I don't have any problem with it. But LiDAR is not the end-all for rock slope stability analysis. Okay? Here's the problem. What kills you are the secondary joints right here, which are parallel to the face of the cliff. You're not going to see them in your photographs or in your LiDAR surveys. This is what causes half of all the dam failures that have occurred in history have been along valley-side regional joints. St. Francis, Fontanelle, Teton, go on and on and on. This most recent one we had down in Brazil just 3 years ago. Valley-side joints are always dangerous because nobody sees them during construction. Glen Canyon is another one. They didn't have a failure, but they spent 7 years and 4,000 rock bolts trying to hold these things down and keep the water from going through them. So in order to see these guys, you would look for huge blocks down here, And then you look at the geometry of these blocks, and what you find is, some of these surfaces are curvilinear. These joints aren't curvilinear. Well, some of the joints are curvilinear. The joints that form in response to stress relief and unloading from the excavation of this canyon or from the retreat of glaciers, things like that. These are all over the Alleghenies, everywhere. Those are hard to see unless you can go up a little side canyon and look sideways. These little we call these re-entries. So when you're mapping someplace like this, you learn pretty quickly when you go out into a new area, there's 3 places I'm going to map. I'm going to map the road cuts, first and foremost, railroad cuts, whatever you got. I'm going to map the channel cuts along the banks of the channel, and I'm going to map any erosional re-entries like this where I can get back in and get glean some detail of the 3-dimensional character of the rock mass. Boy, that's so important. So important. So you can't just set up over here on the other side of the canyon, take LiDAR pictures, and produce all this data. And the critical piece of data here are those secondary joints that are behind the face that you're not going to see on your LiDAR. So just, believe me, when you get out and practice, this is going to come home on you. It's really going to come home on you. And I was very fascinated by those because you would see every once in a while a face like this one where these valley side joints were actually the detachment surface for these huge rock slides that you'd see down here on the base of the slope. And presto, there's your key. This one's just about ready to come off right here. So that would be the worst possible place to put your fire station. That happened down in Silverado Canyon in Orange County when I was in high school. They put a fire station in a location just like that, and a year later the block came down, wiped out the fire station and all the firemen. And no damage 100 feet that way, no damage 100 feet that way, and the county supervisors are going, how did you ever do that? We don't have 500 people living in the whole mountain range, and the 12 firemen managed to get killed. Well, that was lack of appreciation of geohazards. That's what it was. How did they site the fire station? They picked the flattest spot for it. And the flattest spot was where the rock slides had come down and piled up a nice pile of rock. And nobody ever bothered to ask themselves, gee, I wonder how you got a flat spot here in the middle of the mountains. There might be a reason for it. Those are the kind of questions you want to ask yourself. Say, why is that pile of rock here and it isn't over here and it isn't over there? Oh, it's an ancient Indian landfill for helicopter landing pad, maybe. Something. You got to come up with some. That was a joke. You got to come up with something to explain why that aberration is there. Okay. Mapping discontinuities underground. Underground has all kinds of advantages for us because we can really see what's going on in 3 dimensions. Unlined tunnel excavations, like you see here on the East Minneapolis sewer interceptor tunnel, are incredible because you can get in there and you can map everything and you can kind of see what you got going on. And basically an experienced engineering geologist in a project like this is looking for the aberrations. That's what he's standing there looking for. He knows what he expects to see, and that's what he's designed for. The reason he's out there full-time watching this thing is to look for the aberrations. And that's where you're going to get clobbered, is when something changes that you didn't pick up in your exploration program. And so you have so much debris when you're doing an excavation. Look at all this. This is all debris covering up what's going on. So there's going to be things you can see and there's going to be things you can't see. What we want to try and do is constantly draw the situations, sketch them, and what we do today, I always have my my geologists take pictures and then draw with waterproof pens on the pictures. So you draw right on the pictures, and you do that the same day. Don't let your pictures accumulate for a week. You will forget 70% of the stuff you want to take note of. You have to do it the same day. I would always buy them dinner. If they did their reports that day, they get free dinner. Steak and lobster, whatever you want. I don't care. You can eat snake for all I care. But, what I want you to do is record everything the day it happens. get the pictures printed out immediately and tape them together and write on the pictures, this is what I saw, this is what that is. If you wait 2 days, you'll be surprised how much you'll forget. Just wait, there's a lot of stuff that'll get forgotten. Okay, if I have joints that are parallel to a tunnel, I get tension zones along those joints. Joints are zero tension boundaries. Here's one that killed a bunch of people in the Zion Mount Carmel tunnel. This failure was while they were constructing the tunnel. It was about 270 feet long. They had a section where the tunnel paralleled one of their systematic regional joint sets. That's always bad. Always, always, always bad. Why? Well, because you got a zero tension boundary here, a zero tension boundary there, and along this crossbed, you just have the tensile strength of the sandstone right there. As soon as that tensile strength is exceeded by the weight of this block, down comes the block on everybody in the tunnel. That's what happened. 270 feet long. That is a football field. That's a big block. So nobody survived that one. Here's Zion Mount. This is the Glen Canyon Power Plant tunnel, which is a very, very long tunnel. It's oh gosh. Well, they're both over. Well, one was about 1.5 miles long. This one is actually closer to 2.25 miles long. 6% grade, declining to the base of the power plant. And here they had valley side joints, which form the canyon, form Glen Canyon in the Navajo sandstone. And then they had pre-existing systematic regional joints. And you're going to get tension zones along these like I've drawn in here. So the only thing holding this rock up right in here is the fabric strength here, the tensile strength of the rock itself. Now what happened here, they went in and they blasted, and then they'd wait a while because they had people getting killed by rocks falling on them right up at the face when they went in and mucked right after the blast. So they started waiting longer, and the owner of the tunneling company actually got in there and said, okay, I'll lead you guys and show you how to do this. And he waited 30 minutes, and then he went in and they started mucking, and just the vibration of the muckers and stuff, this teepee-shaped wedge right here fell down and killed him. Killed the owner and the foreman and the guys right up at the face. What happened here is they have this joint set intersecting that joint set, and that thing just comes right out. It doesn't come out unless you give it a little bit of vibration going on. That was just enough that the thing came down and out. So this is the kind of case where you're going to have a shield of some sort or spiling reinforcement, which are rock bolts you shoot out in front of the tunnel heading to try and pin these things. And you remember here that any of these things are very tough to gauge ahead of time because there's little nuances in changes in these spacings. And the closer these spacings are, the smaller the wedges are, but the easier the wedges come out. So these are two-dimensional representations that are very simple of a three-dimensional situation where the tunnels were parallel to the strike of the joints. That's the easiest it ever gets. Usually it's not that easy. Okay, so here's another side hill tunnel where we have a tunnel opening for highway, and then we have an annulus between the tunnel right here and the cliff face out here. And this is where the cliff face failed. This line along here, the cliff went kaboom and came down. And what I'm doing here is I'm plotting my strike and dips of my joint sets. And this is just what I was just talking to you about over here a few minutes ago. If we look at this thing, we see we have one set that's pretty tight right here. We got this set that's pretty tight, and then we got this very diffuse set, and that's the one causing all the trouble. So the diffuse set, you're going to have to try this one and see how that goes, and you're going to have to try this one. You have to bound the problem with both of them and take the average and see how those do for you. Now this one I got a lot of surprises on. When I went in here and used an impression packer, I actually put a packer in and went out, I intersected these valley side joints that we didn't know about, And here I had called some of these mechanical breaks when we were doing the drilling. Turned out they were all actual joints running all the way through. I had a cluster of valley side joints right here. I can't explain that theoretically, I just know they're there. It's probably one set started and came this way, and then another set started over a foot or two and then went that way, and so on and so forth. But they all crossed over each other right here, and that's why we had problems right here. Ouch. And so this is real world data. That's how much variance you have with the different suites. So obviously one suite's very, very clean and very, very consistent. Another one's very clean, very, very consistent. Notice that they're mutually orthogonal to one another. And then I got this messy set. The valley side joints are very messy, and they're not nearly as clean. And so, but I've actually got them labeled here. These are the valley side joints, this group, and then these are transitional ones. And the transitional ones were the aberration. So you have a big variation, and that's because these are secondary joints. Their genesis is geologically, they're very, very young, they're very recent, and they're forming in reaction to the excavation of that canyon. So they don't have a clean geometry. They have a highly varying geometry. So that's the kind of stuff that really you have to exercise a lot of judgment on. What we do underground is we make these wrap maps or fracture maps, and we actually unwrap. This would be the crown of the tunnel right here, so it's a horseshoe-shaped tunnel. And we're actually doing here is we're mapping all the discontinuities in their true, how they truly come through the tunnel. So these are coming through at an angle of about 45 degrees when you see them coming through like this. And these other guys are coming across at much higher angles. And so through the tunnel, this is again is a wrap where I'm going from this side all the way up and over to this side, and I can see the three-dimensional character. Now we have all sorts of computer programs now that take care of plotting this kind of stuff. In the old days, this was a bear to plot. You actually had to put yarn on the side of the tunnel, you know, on foot grids or meter grids, and then sketch all this stuff in with the stationing and everything. But you can see it's a very complex three-dimensional problem very, very quickly. And so you can get pretty lost pretty quickly if you don't get in the tunnel and spend a lot of time in it and get a feeling for each one of these. And what we're doing here is we're actually showing, this is the crown of the tunnel, that's the top. So let me, I need to go over here and actually draw that. Hang on. Okay. Where's the thing we were, see? There we are. All right, let's go back over there. We have a piece of paper here. I want to do some definitions here for you because I'm going to be using some technical terms, and you may never have been in a tunnel. So what we have in a standard horseshoe-shaped tunnel sometimes this is done like this with a healthy gradient to it like that. We call this the invert. That's the floor. Where it starts to turn is called the spring line. So that's the right spring line, the left spring line. And then this is called the crown. Now, it isn't uncommon at all for us to do a pilot tunnel, the pilot bore, up in this area. Sometimes they bring the pilot all the way down here, and we call that the pilot bore. And that lets us get in there and see what's going on. And then sometimes we excavate the shoulders after that. So this would be 1, 2, 3, 4, 5, 6. It'd be that kind of a sequence. And then they just start taking it out 7, 8, 9, and so on, taking it out by gravity and taking it out on the invert. So today with tunnel boring machines, which are the norm, we're doing it full face, all at the same time, typically circular. We'd still call this the crown, and we call this the shoulder in that case. And we call this the invert still. So the invert's the bottom. And then you have stationing along the way that you might see on here. So if we go back and look at my section, what you see here, he doesn't have me back on yet. There we go. What you see here is stationing. So these are 100 feet apart. Nope, the stations are on the bottom. I'm sorry. So here's a station. This is at station 1 plus 75. So this particular look that we're getting, this one is another station number down here. So stationing is along the axis of the tunnel, and that tells us where in the tunnel that we are. And this is obviously, computers help you keep track of this. Now here's a real typical one out of a job I worked on where we're looking at quite a bit of the tunnel now. And what we're seeing is we have some very low angle discontinuities coming down here and going back that direction. And then we have very low angle stuff right here that's carrying through for a long distance. And the low angle stuff typically doesn't give us as much trouble with things falling in. That's the steeper dipping stuff that's going to have stuff falling on your head. So you're always looking out for that stuff, especially if you get a tent going like this. But here, which I wanted you to see, is there's your regional dip right there, regional strike and dip. You can see all this stuff is kind of waving in and out through the crown. This is the crown of the tunnel. But we got all these other things running through there too. So in a typical hard rock job, it's not uncommon to have 6, 7, or 8 suites of discontinuities, all intersecting each other at various complex intersections. And these tend to change with where you are in the tunnel. What always gives you a fits with the tunnel boring machine is running through fault zones. And everything changes on the other side of the fault all of a sudden. Okay, block kinematics is what I want to give you a brief introduction to next. And block kinematics are something we talk about a lot in rock mechanics. If you take Professor Mayer's rock engineering course, he'd be talking about a lot of these things. What I'm looking at right here is a toppling type of failure, where you have something that's dipping 55 to 75 degrees. These kind of things can topple over just like a bunch of books toppling off a shelf. And what we're trying to do here is go out and measure planar discontinuities by getting their respective strike and dips. Now the easiest one you might remember from field work is the strike and dip of a planar surface like a bed, like shown here. And the dip is going to be the maximum inclination from horizontal off the strike. The strike is a horizontal line drawn across any inclined plane. And we're relaying that to how many degrees off of north, going to the east or going to the west, typically. In Europe, they just use the azimuth line. So they'd say 065, that's north 65 east. Or they'll say 330, which is north 30 degrees west. And that's like we use in navigation. So this would be one discontinuity suite, the bedding, and then you actually, the plunge of the dip is going to be the maximum line. Now, when you have movements, they very rarely go right down the dip. Usually they have some apparent component going off this direction or off that direction, depending where your road cut or wherever your cut slope is. So if we go out and we look in the real world, it's not hard to see things like dip slopes. A dip slope is structurally controlled by the material that's underneath it. And this is a dip slope by, well, this is Convict Lake over here, where the largest rainbow trout in the history of the world was caught back in 1955 or so. And what we're looking at are all these white rocks. Those white rocks all showed up suddenly in the January 1980 Mammoth Mountain earthquake sequence. That was 4 earthquakes in 1 month over magnitude 6 each one. And all these rocks went down here and went down the slope, and some stopped in this area, some kept on going, some hit the trees down here, some went in the lake. It was really, really very, very interesting. Typically, we call this the angle of internal friction, or the phi angle. You hear the term phi angle. That's how steep the slope can be given the material that it's comprised of. Now, 33 degrees is a real typical phi angle for sand. So if you have a sand pile, the kind of sand you buy at Walmart and put out there for your kids and that the cats like to use, 33 degrees, typical for quartz sand. But when you get into crushed rock, you can get up from 37 degrees for crushed rock gravel like limestone, up to about 50 degrees for very angular rock. So what happens here is you have conservation of momentum. So the bigger rocks tend to fly further, get more kinetic energy, and bounce further and go further down slope than the smaller blocks. And so you also have the rock breaking apart, which takes out some of the kinetic energy as it goes down slope. So some of these blocks, when they did detailed analysis of them and came all the way back up, some of these started out at 100 tons, and by the time they got all the way down to the lake, they were down to 2, 1, half a ton. They'd actually lost like 90% of their mass in the tumbling down and breaking apart due to induced tension as they go down the slope. So that's the simplest block kinematics. Here's the one I always like. I always have the client calling me and saying, Dr. Rogers, we need your help here. We have a road, and this road just gives us fits. It's just, we have all these sliding problems. And I go out and I look at the road, and this is what I see. Well, this is what we call a big duh. Look at that slope. What's going on there? Why isn't anything growing on the slope? Has the hillbilly been out there spraying Roundup on it? You guys are way too serious. Lighten up, lighten up. Drink some coffee, go get a beer at the break, do something here. What's going on?
Erosion.
Erosion.
Still going on.
Very good. Erosion still going on. Yes. Erosion is still going on. So if I cut a slope in here for my road, what's that going to do? That's going to oversteepen a slope that's right at its phi angle. Its factor of safety is 1.01, 1.03, given the environmental extrema to which it's been subjected. That's what the factor of safety is going to be when it's raining a lot for a while. So if you put a road in here, this is just a matter of time before you're going to lose this slope. So all my biggest Department of Transportation problems out west, there they are. If I had to sum them all up for you, most of them look very similar to this, except some of them in California, the raveling here has gone up 1,000 feet above the highway. How do you get up to work on something like that? You don't. You transfer to another office, go to another county. You can't. You can't chase it. What you can do is put a tunnel around behind it or put a cover over it. That'd probably be the smartest thing. But this, you're just fighting time. It's a matter of time before you're going to lose the road. And so it just becomes a maintenance issue. But once these things start raveling and retrogress up the slope higher and higher, once it gets about 70 feet above the slope, you don't want to know what it's going to cost, because it costs more money than you have to repair it. Now, the simple presence of water on an inclined surface significantly reduces the frictional resistance to sliding. So the driving force is increased by the water head acting on the inclined surface, and the resisting force is decreased by the pore pressure. So it's not about the volume of water, it's always about the pore pressure. If you have pore pressure here, you have trouble. So when we cycle lakes, they started cycling Lake Roosevelt back in the 1950s. That's Grand Coulee Dam. It was built just before World War II. And then they utilized it during World War II for the aluminum industry, for aircraft, for Boeing aircraft, making all these B-29s and B-17s and things. And when they got into where they would actually cycle the lake down to keep the twinning process going for the aluminum, they started seeing huge landslides along the lake edge. And that was a mystery to a lot of geologists who didn't understand effective stress theory. They'd say, well, they were looking at things from a total stress viewpoint, saying, well, this is more water. More weight of water should stabilize the slope because it's pushing against the slope, and water's pushing the same in all directions. Well, that's fine until the water table drops. Now the water table drops, you still have the pore pressure over here, because this takes time to drain. So if this goes down more than 12 inches a day, you're going to be in big trouble. And that's what every agency recognizes, and they all say the same thing. Do not fill the lake more than 12 inches a day. Do not drain the lake at more than 12 inches a day. Well, they forget to tell God. And that's what happened with Teton Dam. Teton Dam filled at 36 inches a day. And what could they do about it? Nothing. And it failed on them on the first full filling. Failed catastrophically. So, and they knew at the time that this is not a good thing, but they couldn't control it. They shouldn't have allowed that lake to fill until they could control something like that. That's the bottom line of that. And that was one of the lessons out of Teton. But what you have here, if you have a pore pressure imbalance, you have big trouble. So you can actually let the lake fill up, and it fills fast. That's not going to cause landslides. The reason we limit it to 12 inches a day is so we can evaluate the seepage around the dam and make sure we don't have a big conduit. That's what happened at Teton. And this conduit just, it showed up at 7 o'clock in the morning, and by noon the thing was gone. And they had equipment out there, they had contractors out there, they were just finishing the dam, they tried everything they could do, and nothing worked. Same thing happened at Baldwin Hills in 1963 in Los Angeles. And at Fontanelle on the Green River in 1965. Okay, what I want to show you here, this is a very, very important conceptual picture. I was never shown anything like this in my graduate school education. This actually came out of a conference at Colorado School of Mines, 1958, first rock mechanics conference in the United States. And what it's showing here is the position of the slope dictates the stress regime that you should be interested in. So what am I interested in this week? It depends where you're working. That's what. So there's not a simple battery of tests you run. You're going to run the test that's appropriate to the thing you're trying to evaluate or analyze. So if we look at this, what do we see here? We often find ourselves working in the relaxed zone near the ground surface. That's where we usually find ourselves. We have much lower shear stresses are at work as compared to the deeper zones way down in here. And note that we have a tension zone and a zone of plastic deformation. This plastic zone of deformation down here is where we get into all the trouble. That's where I get into the trouble. And I have somebody down here, a client, who has a pipeline right here. And the pipeline is getting tweaked. It's moving all over the place. And they're saying, what can I do? What can I do? Not much. Not much you can do down in here, because your pipeline in this zone is going to get tweaked. It's going to get moving around. You come in here and dig a big hole, you're just going to make everything worse. So that's not a great idea. So you don't have a lot of options down in here. You're in the passive resistance zone. Putting a retaining wall in this area is going to involve 10 to 20 times the lateral loads that a retaining wall up in this area, in the tensile zone, is going to do. So you can get away with all kinds of things up here that you can't get away with down here. Now, the other problem I've seen, especially with geotechnical engineers who don't have engineering, geology, or rock mechanics training, which is most of them, is they'll look at something like this and say, well, I'm just going to treat this like an equivalent soil. I'm going to run a bunch of Moore circles, put some big confinement on this thing, and get me a diagram of C and phi. Oh, that's nice. If you're in this zone up in here, and you tested it for confinement down here, what's going on down here has nothing to do with what's going on up here. This is in a zone of dilation and release and lots of zero tension boundaries. And so this zone, what's going to get you in this zone, in the stress relief zone, is strains. In rock mechanics, that's what you got to be looking at, is the strains. Strains can be very big. You're not going to get anything transferred across these joints. Everything is jointed out there. Everything. The best Sierra granite is jointed. Zero tension boundaries. It's not soil. It does not behave like an equivalent clay. So you can get into a lot of trouble, and you don't realize what's going on out in here has nothing to do with your Mohr circle plot. Okay, so you got to know the zone of interest you're working in. Here's the simplest one I can think of. This is where the congressional party with Senator Goldwater, they parked their vehicles right here at Glen Canyon Power Plant. These blocks came off and smashed all the vehicles. Had anybody been in the vehicles, they all would have been killed, buried, taken care of. I mean, the vehicles were about that high. They were done. They're very, very small. And you can see the water on these sheet joints coming down and then joining. This is a regional systematic joint. So you have the intersection of a regional systematic and a curvilinear secondary joint. There's your picture. Here's the curvilinear joints, and there's the regional systematic joints, the vertical ones. Okay. You noticed if I sit over here with a LiDAR rig, I might pick up some of this, but not all of them. These curvilinear joints have a terrible inclination. They're right at tan phi. And so they're going to slide out at the slightest amount of pore pressure buildup along here. These things are just going to slide right on out. And what happened at Glen Canyon, they had so many joints there, so many valley side joints, they were running 10,000 gallons a minute seepage through both abutments. 10,000 on one side, 12,000 on the other side. And this thing was just, smoking with water going through. And so you can see the water coming out over here on the well on the downstream. We're hundreds of feet on the downstream side. Here's the water coming out down the sheet joints. So that can easily trigger a failure. That's not going to be real hard. So right here, what you'd want to do is poke some little holes in here to get you some drainage. That's all you got to do. You don't have to drill 4,000 rock bolts. That's what they put in. Why? Well, because they went and asked a bunch of civil engineers. If you have a problem, you go call the civil engineer. They have two solutions. One's concrete and the other one's steel. Both is better. They're both bomb-proof. What do you really need? Drain. Drain? Yeah. How do you design that? Oh, you just poke a little hole in there and put a little casing, slotted casing in, and you're done. How much does that design cost? Well, about 30 cents. Oh, we wouldn't make any money on that. Forget the drains. And you know what? There's no guarantee the drain's going to work. That's right. There's no guarantee the drain's going to work. But a drain is a hell of a lot better than no drain. And if you get enough pore pressure on it, it's going to relieve the pore pressure. You're not trying to drain the whole mountain and start a water company. You're trying to alleviate excess pore pressures. It's not about volume. It's about alleviating trapped pore pressures. That's what's important. Drains are just way too simple for most graduate structural engineers to, it's not on their radar screen. Now there are structural engineers, if you explain it all to them, they actually understand it and get it. I just haven't met too many of them. Most important thing then is, for rock slides, is pore pressure. You trigger pore pressure. Here's a hornfels, a very heavy rock. This rock is a metamorphosed Cambrian shale, and this block has a unit density, the highest I ever dealt with. I think it was about 169 PCF. So concrete, structural concrete's 150. This is way above structural concrete. Very heavy stuff. I'm out here in the desert where it hardly rains at all, and I had a block here that came down and moved about 150 feet. It was right here and slid out during a intense rainstorm. And now if you look behind us, this is a dip slope. This is a whole dip slope right here. And down here, this whole mountain slid off in prehistoric time and went sliding down to that valley in the background and blew out about 4 miles, called a Sturtstrom. What's going on here, it's not about volume of water, it's the fact that the surface, the discontinuity beneath this block got saturated. It had about 30 feet ahead, because that's how high the block is, and that was enough to just slide this thing out. Once it starts moving, it has kinetic energy, and there's conservation of momentum, and it stopped. Now, it didn't hurt anything to go from here to there, but it scared the road department over here, because if they had something this big come onto that road, they're done. they're closed for a long time. Here's one I worked on in South America, where everything's 100 times bigger than in the United States. And what you're looking at here is a shale seam in a bedded sequence of limestone. So this is all limestone. This is a shale seam about 1 meter thick, not even that, 60 centimeters thick. And the whole mountain slid down this thing, and huge landslide dam down here. And then the river filled up behind the landslide dam and then blew it out before I could even get down there to help them on it. Now, luckily, they knew what was going to happen, and they got everybody out of there so that it didn't kill a whole bunch of people. It could have easily killed everybody downstream. This flood, in this particular case, went down about 65 miles downstream. It took out everything, all the highways and everything. And the way we got in here was in a helicopter, and it had to be on a good day, because you don't see very many days like this in the Andes where it looks like that, maybe 60 days a year. Most time it's just socked in. So what happened here is you have a low wetted strength, and you have a strained softening material, an overconsolidated shale. And how did it get overconsolidated? Well, through burial and tectonic activity. So it's very dense, but once it starts moving, it loses strength with increasing strain. We call that a strain softening material. Overconsolidated shale is seams. These little seams are usually associated with all the world's major landslides. It's very, very treacherous stuff. All right. This is the dirty shame, wedge failure. This is the most famous wedge failure in the United States. This was the Walla Walla district of the Army Corps of Engineers building Libby Dam in Montana, up near the Canadian border. Back in the late 60s. This was a mass gravity concrete dam, very conservative section, but they had this big wedge failure here. They didn't foresee it all, and this whole mountainside came down right on the left abutment of the dam, which you can imagine that was a pretty bad event, and it delayed the completion of the dam by 3 years. This was during the Vietnam War. So they had to come in here and put in a whole series of rock tendons, big, huge bolts. And what happened here, you can see this is the bedding plane right here, and this is a joint surface that's almost orthogonal to the bedding. And this is the zone, the intersection. That's the intersection, the wedge intersection. And you can see on this cut slope they made right here, the cut slope was about 1/2 to 1. It's very, very steep. And so this thing came out and daylighted in that, and then of course they had a consultants panel, and the panel wisely pointed out to them, well, this geometry is the maximum wedge you could have for that cut. What about your powerhouse down here? You got the same geometry sitting right on top of your powerhouse. What if you have an earthquake? And so that's why the project was delayed 3 years. And so the Corps of Engineers at that point did a lot of work on how to analyze wedge failures. Now, if we look in any of the books, this is about the simplest kind of wedge failure you'll see, like the one I just showed you, where you have one plane here, you have another plane. They're very, almost never symmetric, and usually you're sliding more on an apparent dip on one of the planes than another one. Sometimes you come down right along the intersection like the one I just showed you, but that's pretty rare. Generally, they look something like this. And you might get a smaller one up here first, and after it comes out, then you get a little bit bigger one. And after that one comes out, you even get a larger one below that. And so in this kind of stuff, when you take a picture of it with your LiDAR, you don't always get the true geometry of these joints. You have to have some sort of exposed face you can put 3 points on to get that, or you have to go out there and actually physically measure it ahead of time if you want to do an assessment of it. But these are very, very susceptible to pore water pressures. So if you get pore water trapped in here along this lower one, so the water comes running down here, gets trapped in there, that's when you get the trouble. Now the one that I get the most often statistically in the mountains is where we have a highway right here, and they are doing snow removal on the highway, and they stack the snow up right here. And that creates an ice dam right in this area. And then they start getting thawing up here in the higher country, and this pore water comes down, flows down this thing, hits the ice dam, builds up pore pressure in the block, and then boom, the whole thing comes out around April 20th. Right around tax time, they always come out. So, all right, here's a simple one looking using a stereo net projection. They're very useful for identifying and analyzing the simplest rock blocks, where their stability depends on the friction, just on the planar discontinuity. So we're looking at a two-dimensional view here, where we have a siltstone unit sitting on top of a more massive unit down here underneath it, and this thing was originally made at a cut like this of 1.5 to 1, and that cut proved to be too steep for this particular place. So when we go in and we do a classical analysis of it, what we see here is we actually have movement of the wedge predicted on the bedding plane from the cut, and that's actually what happened in this particular case. Friction values that I used were between 20 and 30 degrees. Those are very, very commonly used, 30 usually being the higher end, 20 being the lower end. That one wasn't very hard to analyze. Here's another one, a little more complicated, where they have, again, they made the cut at 1 to 1 on this highway, and they have a daylighting plane right here coming down at about a 2 to 1. Or 1.5 to 1, about 33 degrees. And again, if you look at the solution here for the various blocks, 1, 2, and 3, you can see we have sliding on the intersection of the bedding and the J1 plane, because these joints are zero tension boundaries. So it's going to break right there. That's already got the crack there. It's just a matter of overcoming the friction right along the base of the block here. So if this can get water into it somehow, and that water gets backed up along here, out the block is going to come. So you always want to sketch the actual situation and make sure it agrees with your stereo net solution. And these are the simplest ones I've ever worked on in my career. Actually, that's why I use them for teaching. So you see what I'm plotting here. I'm plotting the joints, the bedding, and the cut slope, using those three determiners to try and get a feeling for what's going on. All right, let's stop right there for our quick break, and we'll pick this up in about 5 minutes, 3 minutes or something. what I've got here to show you is a real good example of how you don't want to treat discontinuous rock as an equivalent soil mass. This is a case involving a nationally renowned geotechnical firm in San Francisco. They didn't have a geological engineer on staff, so they got all these soil engineers on staff. So they had to do design for a retained excavation for a large office building, 80 feet high, vertical, beneath an existing apartment building with a gorgeous view of San Francisco Bay. So they decided to assume an active pressure wedge like this with a phi of 55 degrees because the slopes in this area were about 55 degrees, the natural slopes. And they're going to put in rakers, and they decided that rakers would be too expensive and that they would really encumber the building area. So they decided to put in drilled tiebacks. These are actually tendons, rock tendons. And when they did this, their anchorage zone was well behind the assumed active pressure line. They ignored the discontinuities that were sitting here. Now, the reason I'd show you this case history, this is pretty typical, the kind of stuff you see in a lot of big cities. What happened to them was this down here. Their tiebacks did hold this entire block together, so it all came down as one big, huge block, which kept the people in the apartment building from getting killed. But the problem was right here. They had a discontinuity coming down this way and then a low-strength phyllite bed right here that they actually slid on. And the reason was because right here, when this thing started to relax, this is a very large excavation. If you have an excavation that big, you're going to get some relaxation towards it. And what happened is they tweaked the water line right here, the city water line. Now the city water line is something you don't want to tweak. They didn't rupture it. They tweaked it. Tweaking it means it was a ductile steel pipe. It pulled and it started leaking water, but it didn't make a big noise. So they didn't pick it up with the sonic velocity logger, and they didn't see any water coming out of the ground. The city staff, they saw there was a crack here, but they weren't worried because they didn't see water bubbling up out of the crack. Well, the water was all going down here and then down here. And by the time they realized this was a very deadly situation, you got to realize water lines are under pressure. They can leak a lot of water in a short amount of time. If it's been a sewer line, no trouble. But this got too much water, too much head on it, 80 feet high, and the pore pressure got to a point where the whole thing just let go. And what it did here is it slid a short distance about that far and stopped. It went about 20 feet and stopped. But now, what do you do about this? Can you tie all this back together? Can you save the buildings? Blah, blah, blah. The answer is no. No, you can't. No one's going to sign on for that liability. The apartment building was worth about $27 million, and this was bad news. You have to consider the discontinuities and the geology and get somebody on your design team who knows what they're doing. You don't play with something like this and treat it like an equivalent soil. Now, if this had been something with a consequence, this is just a logging road or something, and there's no $27 million building here, fine, go for it. Go ahead and cut the slope, and it fails, you clean up the mess. But if you got a $27 million structure on top of the mess, that adds a lot of cost to your project. By the way, their total fees on this job were about $27,000. Pretty small job, even for that company. All right. Part 10, dangers posed by valley-side joints. I've shown you this picture before. This is the glacial cirque of Little Shut-Eye Pass in the Sierra National Forest. We're just south of the Yosemite National Park boundary. This is the Mount Givens granodiorite, which is a very, very strong material. Now we're going to go up to Norway, to Lone Lake. And at Lone Lake, this is a fjord, former fjord, and it's landlocked because the mountain failed, came down, and built a dam between Lone Lake and the open sea. So we call it Lone Lake instead of Lone Fjord. And there was a town over here on the other side. And in 1905 and 1936, the cliff detached itself along valley-side joints and came roaring down. Here's what it looked like head on. This thing came down on valley-side joints, came roaring down, and hit the water. Now, water is relatively incompressible. So what happened is, this came down, hit the water. They had a huge seiche, like a tsunami wave. From that, the wave went across and wiped out the settlement on the other side of the fjord, other side of the lake, killing 73 people. Now, when they started studying these sorts of failures, they found they're fairly common in Scandinavia. And the Norwegian Geotechnical Institute down at Oslo, NGI, found that 70% of their rock slides in Europe occurred during the first fall freeze or the first spring thaw. What's going on? Pore pressures, pore pressures, pore pressures. This is all about trapped pore pressures. It's not about the volume of water, it's about pore pressure. And when you're dealing in this kind of environment, you get 0.414 psi for every foot of elevation. Look at the elevations here. This is probably about 4,000 to 5,000 feet high. That's some big pore pressures. That's way like 10 times what Hoover Dam is. All right, valley side joints are a chronic headache when we're building dams. Because when we get in to build a dam, by definition, this is what happened at Teton, we want to take off all the loose material. Any open joint, by definition, has got to be taken out, and we got to clean this surface off so that we can put the dam against a nice clean surface. And this is showing Mammoth Pool Reservoir, built by Southern Cal Edison back in the late 1950s. They brought Carl Terzaghi, the father of soil mechanics. This was one of his last consultations. They brought him in on it, and every time they excavated these sheet joints at this dam site on the upper San Joaquin River, they would have new ones that would form, that would pop off. And they're getting all this rubble zone along here, and they're digging, and they're digging, and they're blasting, and they're digging, and they're drilling, and they can't get out of these things. And Terzaghi was a very wise kind of a fellow. He only had 160 consultations in his lifetime, but he studied each site in great detail, and he had a wonderful background in geomorphology. He was trained as a geologist and as a mechanical engineer. And he's the father of modern soil mechanics. Wrote the first textbook on that subject called Erdbaum Mechanic when he was teaching at the American Robert College in Istanbul, Turkey. And he started teaching there after World War I ended in late 1918. He was an Austrian engineering officer during the First World War, and he had worked in the United States 4 years on various dam projects prior to the First World War. So he was very learned and well-traveled, and he wisely told him here, you can't win this battle against these valley-side stress relief joints. What you need to do is just stop here and go ahead and put the dam in to get the confining weight of the dam to push these things back down as much as you can. You're never going to get them pushed all the way back down. What you're going to have to do is come in here and drill afterwards and grout all those joints, those valley side joints. Grout, 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 grout. And that's what they did. And this project's been very successful. Valley side joints are always treacherous because they're usually inclined at close to 45 minus phi over 2, like you see right here. 45 minus phi over 2, if phi was 30, would be an inclination of about 60 degrees from horizontal. If you're at 60 degrees from horizontal, that's a very bad inclination to have a toe kick-out failure like this, where you just have this big, huge block, falls down, and you see all these house-sized boulders down here down below, which look like this. So if you're seeing gigantic things down here, you got to ask yourself, hey, that came from right up there, right? So this gets covered up pretty quickly with trees, and the rock gets patina of weathering on it, and within 100 years, trained eye won't, you need a trained eye to recognize what happened there. This is what it looks like the day after it happened. This one is at Gallery 6 at Zion Park, and that one was about 83,000 tons that came down in one event. Here's one I showed you a little earlier on the Colorado River, down around 6 Mile Wash, came out of the Kaibab limestone. This is a joint face here and another joint face there. That's a wedge failure. And when this block came off, this one is a very large wedge, but I want you to see here is how it just disintegrated completely from just dropping a couple hundred feet. And it just disintegrates, and you get this big, huge talus fan. Now, if I'm a mountaineer, this is what I'm always looking for. If I have this escarpment right here, see this escarpment in the Toroweap Formation? How am I going to climb above this? Well, I'm going to look for a rock slide. I'm going to get my backpack, and I'm just going to stitch my way right up this. And that's how I'm going to get over that escarpment. And then here, I'm going to walk along this escarpment till I find some similar place. I might be able to actually get up right over here, come across there, work my way up, get on these blocks, and work my way on up right there. So that's the kind of feature you're always looking for to get across an escarpment, a vertical escarpment. Well, here's Fontenelle Dam. This is the closest we ever came to having a real first-class disaster. That it's the exact same failure sequence that occurred at Teton 11 years later, not very many miles away, actually. This is on the upper Green River in the Wind River Range, and you can see a 10-wheel dump truck for scale right there. This is their main spillway. This is the right abutment, and there's your leak coming right out of these valley side joints in the right abutment of the dam. In this case, that was the lake level right there. The lake didn't fill as fast as Teton had filled, so they were able to save it just barely. They just barely saved it. And then those guys retired. And if we look in the right abutment, now we're on the other side of the dam, looking downstream. Here's the original abutment line. There's where the hill originally was. This is their over-excavation for the dam. And what happened in here, they had these valley side joints in the Green River Formation. And the Green River Formation is a sedimentary rock. And in pure geology textbooks, they preach, and I was a victim of this in school. They say, well, we don't get valley side joints in sedimentary rock. That is false. You go out and look for them, they're there. They're just harder to see because sedimentary rocks are so regularly jointed already. So they came in here and did 8 lines of grout holes and ended up putting in 203,500 sacks of cement just in this one area, trying to fill all these joints up, and they haven't had a problem with it since, and that's 45 years ago. But that was a very near catastrophe on a major river, the Green River being the major arm of the Colorado River system. This is the Camara Roll Creek Dam in Brazil, which failed in July 2004 on its first initial filling, made out of rollcrete, which is the best material we have out there right now. And again, these are valley side joints that it failed on. You can see this is before the dam collapsed into the hole, but there's the valley side joints. The seepage came around, went through those, undercut the dam, and then the dam fell into the hole on its first initial filling. So that's excessive seepage along these valley side joints. The reason you have excessive seepage is the open joint. So you're not going to get any head loss as you flow through it. That's a dangerous situation. So in this case, they did not do a good job of building a grout curtain up their sloping abutment with uplift relief wells downstream of the grout curtain. That's been a standard detail on all American dams since the late 40s. They chose not to do it there because they thought they had a very good rock material. This is back to Zion, again, to look at the Gallery 6 failure. This is my reconstruction of what the cliff looked like when they built the tunnel in 1930. This is the solid line is what it looked like after they had the rock slide, and you can see that the tunnel is daylighted right there. And that's the tunnel opening right here. And so they lost a block here that was gigantic, and these are the valley side joints that you see coming down that are controlling the slope morphology that you see here in these various columns. They're all at different stages of cliff retreat. So if we actually look at the big picture of Pine Canyon, we have stress relief joints over here, and we have stress relief joints over here, and this is a non-glaciated canyon. This is down near the Arizona-Utah border, southern Utah. It's not a glaciated area, but it has a cross-section that kind of reminds you of a glacier. It has kind of the U shape. That's because of the valley side joints. And here's Pine Creek down here in sight in the base of this. When we come up this side and we climb up this slope, what we find is all slide debris. It's rock slide debris all the way up to here. So these things are failing periodically and splattering all this rock debris on the slope. So you don't have to be a college graduate to figure that one out. You just got to get out there and try to hike over these things. And some of them are 60, 70 feet high. That's tough hiking. And you get over this one block, and there's another block 70 feet high. You can't even climb over the things. All right, I want to go back and show you something there I forgot to show you. When I helicoptered in, come on. When I helicoptered into this area right here, these valley side joints, some of these were 6 feet across. They were open. Because this thing is 2,000 feet high, these were actually separated. They were just huge. You could drive a Jeep into them. They were so open. So runoff is going to come down these things and come down here. And it's going to get stopped right down in this critical area right here called the shoulder. Well, what I did is, if we look at an oblique angle, here's where the failure occurred. That's the scar, what it looked like about 21 years after it occurred. And now I'm going to do a head-on view of it. And using terrestrial photogrammetry, I'm going to call this column 1, column 2, column 3, 4, and 5. Now column 5 is this one right here that really sticks out. And column 4 is the one that it goes back the furthest. So this one's very curvilinear. That's a valley side joint all the way up, that column 4. And column 5 is a regional systematic joint. It's near vertical. And it sits out here about 250 feet in front of column 4. This is column 3, which failed in 1958, as intermediary between those two in terms of genesis. So if we look at stage 1, stage 1 is what happened at column 3 in 1958. You had a major failure here. You now have an overhang up here that scares everybody to death, and that should. And you have this enormous block here that came down and splattered all over the slope, leaving all this rockfall debris. If we look over here, stage 2 would be what we see at column 5. That's when this overhanging piece falls off, and that will. You get an earthquake or something, that's going to come off next. It's going to splatter all over this area and fracture the toe right here. The toe is already fractured. And then it's going to look like this. It's going to be a nice, clean face all the way up to the top. So that's, I call stage 2. Stage 3, you get more, because of this failure, or this overhanging part dropping off, you have a stress relief zone up here, and you get more valley side joints now coming down and concentrating in this turn right in here. And that's what's going on in stage 3. Stage 4 is what exists right now at column 4, where it's very curvilinear coming down. This is a joint surface, and it's a secondary joint. It's curvilinear instead of being a regional joint. And so that's pretty similar to what you had going on at column 3 before it failed in 1958. And this is what column 3 looked like right before the failure, when they had dug the tunnel right in this area. They had these overhangs coming out, about 3 of them, which are very prominent. It's undercut right here, and this is where the failure occurred along a regional systematic joint, and then it kicked out on this curvilinear valley side joint. All right. Part 11 is toppling of rock slopes. This is a topple that was sketched by Alexander von Humboldt when he went up the Rio Magdalena, which is now in western Colombia, back in 1797. I was working in the Rio Magdalena on hydroelectric power project dams when I was in graduate school for the Republic of Colombia Hydroelectric Authority, and I went back and looked through von Humboldt's original materials and found these are columnar basalts. And he actually faithfully drew this toppling failure in there several hundred years sooner. He was the first European that went in there on scientific expeditions. And of course the Humboldt River is named after him as well. Whenever you have a block that is shaped more like a rectangle and the resultant W passes outside this corner right here, if it's outside the corner, you're going to tend to get a toppling failure. If it's inside the corner, you're going to get a sliding failure. So toppling failures are very common when you have regularly jointed or regularly foliated massive rock where you have these low friction discontinuities between 50 and 70 degrees. They can be joints, bedding, or foliation. What kind of rock is most susceptible to land slippage? Believe it or not, it's mica schist. Mica schist, absolutely the worst for large bedrock landslides. If we look at the Lhasa, Tibet to Kathmandu, Nepal, Friendship Highway, massive slides on that. Keep the highway closed 2/3 of the year. Most of them are in mica schist and other metamorphic rocks. These are rocks that are heavily tectonized in the Hindu Kush, but the slides are just giant wedge failures and toppling failures. Flexural toppling is actually very, very common. It's been called slope creep for so long by a lot of geologists. They don't even realize. They just call it, well, it's plastic flow. What it is, flexural toppling occurs when the length to width ratio of the adjacent blocks causes the center of gravity to flip over. And it starts down at the toe and it works its way back up slope. And what happens is the sum of the strain increases as you go up slope. So once a flexural topple, like right here, this is at Clear Creek in the Grand Canyon, if you watch these things, very slight deformations here, greater, 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 greater. You get to the top, they're the greatest. So there's the foliation, there's the plastic deformation. And you see the change in dips about 40 degrees, 50 degrees. That's because strain accumulates up slope in landslide processes. So if you put an inclinometer up here, you put one in the middle, you put one down at the bottom, you're going to get different readings in all of them. It's all the same slide. Doesn't mean one part's moving more than the other. It's the accumulation of strain that you get going up slope. So they're very easy to recognize up in here. And right up in here you get hinge lines, and they get mapped as faults all the time by geologists and structural geologists. What they are, they're listric fault surfaces. They're landslide detachment plains. Very, very well developed in the Zagros Mountains, western Iran, where they're huge features, and the pipeline complex in the Franklin Mountains north of El Paso, very similar. And they're in sequences of bedded limestones and shales in both places. Slope creep can often be seen when you look at the staining, iron staining along a joint, and you come up and you get into the weathered regolith up here, and you can actually see it turning and plastically deforming, because this material has a lower modulus of deformation, much lower. So these things come up out of the bedrock, go into this old cemented colluvium, and they curve over under the influence of gravity, pulling that stuff slowly down slope. Here's what a flexural topple looks like. This is another one out in the Grand Canyon region. I had a National Science Foundation grant back in 1978 to go down the canyon and map these things using terrestrial photogrammetry, and I was just overwhelmed with how many of them we found. We knew about one only, and we ended up finding about 26 different ones there. But this you can actually see, there's the hinge line right here. And what's happened here, this is an untoppled surface, and the toppling failure probably got triggered by an earthquake, and it detached and just catastrophically went down in the canyon. And we're over on the right edge of that slide right here, and we see this dilated zone that's turned over very, very dramatically. All kinds of open fissures and cracks. You see open fissures and cracks in a Precambrian schist like this. That's only one thing going on. That's a rock slide. This thing is failing. You got these big, huge cracks in here. We call that dilation. So this thing is moving over, and the next big earthquake, this thing's going to detach right there, and the whole mass is going to go sliding down the hill. So what you're seeing here is a fabric change. You got very, very steep foliation right here. Comes up, turns over. A lot of these things get mapped as faults, and they are. They are faults on a small scale. They're detachment surfaces. Toppling can kill people if they're on the road when the mass comes down. That happens. Rain usually is a trigger, or earthquakes are a trigger for it. And if we look at it, we model most of these today using the program UDEC. UDEC is very useful for mapping complex jointed masses, turning on gravity, and here you go. You see you get upslope facing scarps when you have toppling failures. And then you get these zones of dilation and relaxation that come up the slope. So how far back do you have to be? Well, way back here. This whole zone is involved in the topple. So the topple initiates down here, but it ends up affecting a very, very sizable wedge of material. This is a finite element program. Okay. Part 12, rockfall hazards. Probably the most difficult consultations, some of the most difficult consultations I had to do for highway departments were rockfall hazards. This is what it would look like when they called me. They said, oh, go out there, but I wouldn't go out there till next summer, you know, go out at your own risk. Or we don't want to tell you to go out there. Well, how am I going to do a consultation for you if I don't go out there? Fly over in a Black Hawk helicopter? I can't do that. They're all in Iraq. We don't know Black Hawk helicopters around. I have to get my Icarus wings on or something, or fly around in an ultralight. But anyway, you have to get in there to see what's going on, and you got to be careful. I had one a couple of weeks ago in Santa Barbara that was the scariest one I've ever been on, where I was actually scared of getting killed by a rock slide. This thing was just actively raveling onto the coast, and there was nowhere for me to go without getting real wet. Rock falls are common problems in highways and mountainous terrains. This is one on Interstate 70 in Glenwood Canyon. No highway was built with more engineering. Took 20 years to design. Won all these awards, and it's been pelted and closed repeatedly by the rock falls. Reason? High energy. These things come down. They pick up a lot of kinetic energy, and they go into these pre-stressed double T sections and just snap all the tendons and blast right through them like they're bombing attacks being run by the Air Force. And so they're very problematic. The most problematic stuff I deal with, though, is glacial tills. This is what you have all over the Hindu Kush. You have glacial tills. Glacial tills are like trying to get C and phi values on landfills. It's impossible. Why? Because it's a heterogeneous assemblage. That's big college word for a whole bunch of crap of all different kinds of sizes and roughness. So if you drill a hole here, can you drill a hole in this kind of material? No. Then how do you come up with strength parameters? Through back analysis. Look at the slope. How steep is that slope? It's pretty steep, Bob. How high is it? Well, it's pretty high. But these materials are plucking out when you have a lot of moisture, a lot of rain on it. This kind of a road is going to be a very high maintenance, high hazard road. Can you keep it open? Yeah, you can keep it open if you have enough skip loaders and enough workers and enough places to just pick this stuff up and dump it over the side. If you want to come along here and do something to hold these boulders on there, it's going to cost you some money. Now, are there people who do that? Yes, they're in Switzerland. Mostly. Switzerland, they charge 3.5 times to 4.5 times what we charge in gasoline taxes. Where does all that gasoline tax money go? Into their roads. Why? Because everything in Switzerland is very, very mountainous. So if you want to get good analogs for how to tackle these kind of things, get over to Austria and Switzerland and look at them. And you won't see unsupported cuts in glacial tills like this, because they know doesn't work. It's a maintenance nightmare. And they have everybody gets out on the roads. When the weather is nice, there's like a national law. They have to all go out if the sun's shining. They all come out and go out and enjoy God's creation and nature and all that. It's not like America where every kid's got a DVD player and is addicted to it, you know. They go out and they get on the highway. So they have big demand for recreation and for tourism. So they have to keep these mountain roads working. So rock falls, 70% of them, as I said before, occur during the first fall freeze, the first spring thaw. This is all about pore pressure problems. So it's not the pore, it's all about the pressure, not the volume of water. So these blocks that are sitting here right at the edge, if they get enough pore pressure built up around them, out they come. So in order to keep these things in place, you have to use soil nails or rock anchors with mesh. And it's a lot of fun drilling these things because you hit a block like this and your drill stops. So very, very difficult to attack these things from a practical point of view. There's all kinds of rockfall mitigation programs out there. Almost all of them that I know of are very flawed. A lot of them are way over-conservative. They show blocks that are wholly elastic that just bounce around like they're baseballs from a ball game and come way out here. In reality, there's a lot of things going on here with energy dissipation with each divot as these things go in. But basically, you've got to have some place for them to go down here where you can get behind this barrier and you can muck this material out periodically because it's a maintenance headache. And if you have a highway department or a railroad, you have dedicated staff to handle that kind of stuff. If this is a subdivision down here with a bunch of California attorneys living in it, they don't want to hire anybody to do anything up here. And they're just going to wait till it kills somebody, and then they'll sue somebody. Because that's their salutation in California. I'll sue you later. That was a joke, kids. Wow. You know, you got an engineering audience. So doing nothing is just going to get people killed. You have to be proactive on rockfall mitigation and have some way of picking this stuff up and mucking it out before it does kill somebody. Sometimes we use rock bolts with mesh to do that. So here's my early rock bolt with mesh jobs. I like using the McAferry mesh because it's triple twisted. Some of it's double twisted. You can also get it coated with a PVC if you're in a marine environment where you have salt air. And you can drape this stuff over a raveling cut. This is one in Montana many, many years ago. And then we can come by years later and we can actually see the loose blocks that have been caught by this. And that prevents them from free falling down here and splattering some tourist bus down here on its way to Yellowstone, which is why we did this one. And so You can see right there, I got some loose blocks sitting right in here, and some over in here. So, costs a lot of money to do it. I have posted on my website the details I've done for the Transportation Research Board Highway Geology Symposium back in 2003. Everybody uses these details. I don't have them copyrighted. They're out there. We developed them over years and years of doing these kinds of jobs using the hollow core rock bolts, which I learned about from the Corps of Engineers. And I am a big advocate of hollow core rock bolts because I get a much, much greater grout penetration and much higher anchorage with them. Far and away exceeds just the regular thread bar bolts. But you have to tell the contractors and have them sign all sorts of affidavits that they're bidding hollow core bolt jobs, or they'll miss it. Okay. That's where I'm going to stop with rock mechanics today. Do I have any other questions that we can field before we talk about our next writing assignment? Yes?
You were mentioning the earth tides or something like that earlier. Mm-hmm. Is that because of the moon or other things?
Yeah, earth tides are because of the lunar pull. Yeah. And they discovered those back around 1960. USGS, or Bureau of Mines, people working with the USGS, instrumenting joints opening and closing in caverns, in limestone caverns. So it's something that's really tough to model, but what it's telling you is you do have a cyclic loading every day where there's an opening and a closing and an opening and a closing. And I showed you the impact of load cycling on tensile strength of rock. Yikes. It's dramatic. So when we say the tensile strength of the rock is such and such, well, that's for one cycle of loading. What's the tensile strength for 2,000 cycles of loading? Well, the answer is something a lot lower. So rock is very weak in induced tension cyclic loading. And there's your problem. So whatever we do, wherever we get out on a rock slope and do, like if we go out there and we scale it, let's say this happens all the time in urban areas. We had a case in San Francisco years ago. I arbitrated as the judge. They had gone out and they had done all this scaling, and guess what? 17 years later, they had another block come off that careened into this restaurant and creamed it. Well, duh. I mean, you did a tune-up on your car and you put a full tank of gas in it, and how's it doing 17 years later? You had 17 years of weathering, of freeze, thaw, and creep, and water going in, water going out, and load. You have to. If you're going to scout and scale a slope, you're going to have to go out and do it continuously. If you got people working under it, and this happened at Hoover Dam too. We had some rock slides that were pretty nasty, serious slides that did a lot of damage. And there have been a number of slides that have actually landed on the powerhouse roof and other places, done damage. And thank God we haven't killed anybody yet. But if somebody had been out there working, they would have gotten killed. Yeah. So they went in and did the first rock bolt job in the United States was actually for the outlet works on the Nevada side at Hoover Dam in 1954. Because they had a big wedge there, it started coming out on them. And they said, geez, what are we going to do here? So they rock bolted it. And since then, they put rock bolts all over the place on a lot of different projects. Yes?
Those like tension bolts?
Yes, yeah. So they're on the website. I don't know if they're listed under this course, or probably are under this course on my website. It's about a 7-page handout. And it's basically, writing, giving us my perspective as a construction manager, contractor, installing these things in all these different situations. What are the things I learned in doing that? About non-shrink grout, about how you pressurize it, and how you watch it. Non-shrink grout's a horrendously expensive stuff. It's really expensive, like $100 a gallon. So it's you definitely want to have somebody doing it who's very knowledgeable, so you don't lose your investment. So things you don't do often are the most difficult things because you don't have people on board who know how to handle those things. Okay, any other questions before I move on? I got a few minutes left. I want to talk about the next writing assignment. I want to keep you going on writing assignments. We have logging a rock core and determination of the rock quality index. I'm going to put that core box in the northeast corner of 265 McNutt, and I'll try to keep the room open. If the room's not open, come get me in 157. That's my office. Or go see Patty Robertson in the department office in 129 and get her to open 265 for you. There's going to be a core box there. The reference items are on the assignment sheet. I should have a GSA rock color chart there. Please don't steal it. They don't make them anymore. I keep replacing them. They're $85, and I can't buy them anymore. So don't steal the rock color chart. I just want to expose you to it. And then there's a steel tape measure. Please don't steal that either. And then there's the box of core. It's 10 feet of core. It's Navajo sandstone collected in Zion Park. Try to read the Don Deere articles. The first one's called Technical Description of Rock Cores for Engineering Purposes. That was done for the Department of the Air Force for Nevada Test Site back in 1963. And then 1988 article by Don and his son called Rock Quality Designation Index in Practice. And that's an important one to read for how it's applied today. So I want you to do that. And you should have finished the limitation of liability clauses. And I want you to then start on course documents on engineering and geology registration. Now, for you distance learners, you do engineering and geology registration for your state. You don't have to do it for Missouri. I want you to know about it for the place where you work. Not the kids here are from Missouri, the students here, but for the distance learners, you can be for wherever it is that you practice. I think 38 out of the 50 states have geology registration now. Not all of them. All 50 states and all U.S. territories have the same, pretty much the same engineering registration. California is the big exception. They have additional examinations for surveying and for seismic loading principles, as well as the Business and Professions Code. So they get to take 4 tests. They take 3 tests on top of the National Civil Engineering Examination. So I want you moving forward on those things, and you should be setting up times where you're talking to each other just like you're in a company. So those of you that are over in civil engineering, those of you who are over in geological engineering, you should be talking to each other about these assignments and saying, what are you doing on this, or what are you doing on that? You know, work with each other. Don't try to, and see what you might learn from discussions with each other about how to answer these things. I don't want you doing things in a vacuum. When you go out in the real world, what's going to save you is your networking and communication skills at the company you work in. Otherwise, you're going to come up with something that's really corny. Like the first job I worked on, I tried to impress the structural engineer I was working for, great old guy, and I did a bunch of mathematics on figuring the area under all these complex curves. And he looked at me like I had AIDS. And he goes, "What the heck are you doing, kid?" I said, I didn't say this, but I was trying to impress him with my college mathematics ability. And he says, "We don't do stuff like that. We draw it on graph paper, we shade it, and we count the squares." Boy, that's low tech, isn't it? You think about it. If you shade it and count the squares, even if you miss one square, you're going to be RDC, really dang close. But if you do it all with mathematics, how are we going to check your work? 3 pages of mathematical equations. Good for toilet paper. Good for starting a bonfire. How do you check it? It's very hard to check unless you're a math professor. I don't know any math professors ever work for me. So you want to always have a graphical solution that you check against the mathematical solution. That's just smart. That's wise. That's somebody who's been around the track a few times and realizes, and basically good bosses will look at an answer and go, "That's wrong." And the young person will get all mad. I did that to one of my young engineers once. He was like a year out of college, and he was doing some area calculations for me on a forensic consultation with a class action suit with some condominiums. And I just knew his numbers were wrong because there wasn't that much land area out there. And I said, you did something wrong. You're off by an order of magnitude. And, oh, he got real upset with me because I didn't even review his numbers, And anyway, so I had somebody else look at it, and we found where his math error was. Was in going from feet to yards or something like that, where he forgot to multiply by 12. And he was off by 12-fold, So that's what judgment's about. That's why you don't want to do things in a vacuum, because your boss is expecting a certain kind of thing. You want to do as much as you can to find out what boss is expecting, so you deliver that to him. So that means you got to get out and network with the people you work with, either at lunchtime or beginning of the day or end of the day. Most good companies have these end of the day sessions where they try to solve the problems while the problems are hot. Doesn't do any good to solve them, weeks later. You want to solve them while they're hot and discuss them. And you got to realize there's always many different ways of solving a problem. There's no one way. Your boss may be somebody who has his particular way or her particular way of solving them, but in reality, there's always many different ways of solving a problem. There's never just one way. If you're at a company where they think there's just one way, go find another company, okay? And what Ralph Peck said, who was my mentor for almost 30 years, Ralph thought it was very important for people in the private sector to work at least 3 different places in their career, so they got the perspective from different size companies. Large companies in particular will tend to have a lot of blind spots. They won't go out and get consultants, whereas a little company will. I had a little company, and we had all kinds of consultants we used, especially on corrosion and things where we're highly specialized. We had to go out and find a consultant and say, should we be worried here or should we not be worried? That was worth $600 or $700 to me, to have that guy tell us whether we should be worried or we shouldn't have to worry. And usually they know. So you want to get perspective working for different agencies. The biggest blind spots I saw were people who had worked by themselves for their whole career, and they'd never worked under anybody really good. So they didn't have good habits, and they didn't have anybody to bounce stuff off of. There was this one guy, he had done very well in the Bay Area, but he was quite lonely, and he would come by my office all the time. He was actually a competitor to me, technically, but he would come by my office fairly regularly just to bounce things off of me, because he didn't have anybody to talk to. He'd say, I got this job, and da-da-da-da, and I want to do this, but I got burned a couple years ago and got sued, on something similar to this. What do you think of that? And I always tell him, well, if you've gotten sued on it, and you're doing it for somebody who's not going to go out there and notice it when it's broken or do anything about it, you can't cut corners on that kind of stuff. You have to do it more conservatively, because they're a low-end user. They're not going to see the broken pipe and judge it for what it really is, and then they're going to wait till the problem is acute and the house is destroyed, and then you're going to get sued. So if there's a real damages, you're going to get sued, whether you had anything to do with it or not. That's the sad part about working in those kind of environments. So just have discussions amongst yourself, but don't just copy somebody else's work. Then you're defeating the whole purpose of the class. What I look at is effort. I don't look at your answer. I don't really care what your answer is. I look at effort. So if the book says, you can make the cut 74 degrees and you got 64 degrees, but you got basically, you did everything pretty well, you tried to plot everything, that's an A for me. Why? Because we don't cut things that close in this business. You want to be in the right ballpark. And all I'm trying to do is expose you to all these things. I'm not worried about whether you get the exact answer in the book. We got that clear? I'm looking for the effort and whether you did original work. Okay. Any other questions? The rock core thing, I need to send out to you on, I don't know if we have a sample. Do I have a sample rock core? I have technical description of rock cores. Okay. Sample rock core log. Yeah, it's there. It's loaded on course documents. So that's what you download to use. And I also have a write-up on stereographic projections that I've loaded that you should have been able to look at. That's on course documents as well. So it ran through the stuff that I did over here for you today. So I try to improve this every year and have the things there based on the feedback that I get from everybody. So next week we will be starting on slope stability, which is chapter 6. So we'll make some assignments on that next week. But for this week, let's finish up the homework on rock mechanics. Okay, that's all I have.